Calculus, welcome back. Last video we were going to do the trapezoidal rule as well. We kind of got cut short, but we're back, and we're going to talk about what may be the final new topic of the year, which is a topic called the trapezoidal rule. This does have a section in your textbook. So I want you to think back for a moment to when we first started the concept of integration. And before we learned anything about the fundamental theorem of calculus, we learned how to estimate the value of a definite integral using a technique called a Riemann sum. And we learned how to do a right-hand Riemann sum, a left-hand Riemann sum, and a midpoint Riemann sum. And all three of those involved dividing the area under a curve into a series of rectangles, okay, and then adding, finding the area of each rectangle and then adding them up to get an estimate of the area between a curve and the x-axis. Okay, so a Riemann sum, in short, involved approximating the area between a curve and the x-axis using rectangles. What the trapezoidal rule does is we're going to estimate the area between the curve and the x-axis using trapezoids instead of rectangles. So the concept is the same, and it's just as simple. Now everything that we do here is going to be using the same principle, that I just talked about. We're going to take an area and we're going to divide it into n trapezoids. We can choose our value of n, or we're given our value of n. We can divide an area into 4 trapezoids or 10 trapezoids, however we want to do it. So I'm going to start, first off, let's just get this out of the way first. The area of a trapezoid, if you don't remember, is 1/2 times the sum of the bases. I'll write that as b sub 1, b sub 2, and then times the height. Okay, so that's the geometric formula. You probably remember that from geometry, the formula for the area of a trapezoid. Okay, now what I'm going to do is first I'm going to just draw a picture. Not really have any numbers up here just yet. We'll draw a curve that looks something like this. We'll call that f of x. And we're going to approximate the area between the curve and the x-axis from A to B. And what we do here is, so I'm trying to estimate this area right here, that shade. I'm not going to shade it because I'm getting ready to draw a trapezoid, but it's this area right here. Okay, now we know now that we can find the exact value of an area like that if I know the rule for that function. I can use the fundamental theorem of calculus to integrate that function and find the value of the definite integral from A to B. So, but what we're going to do is we're going to do this using a numerical integration technique. Okay, both Riemann sums and the trapezoidal rule are called numerical integration techniques. They don't have anything to do with like using the fundamental theorem of calculus. There's no antiderivatives or anything like that. So let's just draw maybe a typical trapezoid under here. Let's say that one subinterval goes from here to here. And so what we do is we draw up to the curve from both endpoints of the subinterval. And then what I do is I connect those 2 points where the edges of the subinterval connect with the curve in question. And then I draw and I'll maybe use a different color here. I draw just a segment to connect those 2 points at the top there. So I go straight from here to here. If you notice that follows the curve pretty well. I mean, with the resolution of my pens that I'm using here, you can't really even tell the difference between the top of the trapezoid and the curve along that region. Okay, and see, so then let's look at this. This right here, we have to think about that. It's a horizontal distance, but that's actually going to be the height of that trapezoid, because remember, the bases are the 2 sides of the trapezoids that are parallel to one another. So this vertical edge of the trapezoid and this other vertical edge of the trapezoid, those are the 2 bases of the trapezoid, and the distance between the 2 bases is called the height of the trapezoid. So I'm going to label that distance with a lowercase h. Okay. Now, the length of this base is simply, the distance from the x-axis to the curve here. So that's just going to be the function's value at that point, right? So for whatever x value is right here, this distance will be f of that x value. I'll just label this as x sub 1, and this as x sub 2. And so then the length of this base right here would be f of x sub 1, and the length of this base right here would be f of x sub 2. And if I wanted to write an expression for the area of that trapezoid that I have here, the area of this trapezoid, it would be 1/2 times f of x sub 1, oops. Teddy, can you see this okay? Plus f of x sub 2, and then times the height, which for now I'll just say, Teddy, can you look at the screen and see if you can see this okay?
Yeah, if you knew what it meant, you'd probably know.
Okay, alright, yeah. Okay, so now let's get down to business here. What we're going to do is I'm first going to just derive the rule for a trapezoidal approximation, and then I'll show you kind of how to do it in the real world or on an AP exam. Okay. Let me erase this. And let's draw a very similar picture here. This is going to be super duper simple. So this is going to be the curve f of x. Here's A, here's B, there's the area. So far it's exactly the same as what I had before. Now, the only difference is we're going to do a little bit better with our height here. So the distance from here to here, we call that h in the last picture that I drew. You notice that's just a horizontal distance from A to B. So that horizontal distance, the height would just be B minus A. Okay, I'm sorry, I said the height, that's wrong. But the horizontal distance all the way there is going to be B minus A. Now, remember, just like with the Riemann sum, I've got to decide how many trapezoids I want to use here. I can use, as many as I want, I suppose. But we'll keep it reasonable. Let's say I'm going to use 4 trapezoids or something like that. But if I haven't decided yet, the number of trapezoids is going to be n. So I'm going to write n equals number of trapezoids. So if I divide this distance, B minus A, into this many different trapezoids whose heights go along here, then the height of one trapezoid, okay, of any trapezoid is just this distance divided by how many trapezoids I have. So for instance, if I were going to use 4 trapezoids, the height of each trapezoid would be B minus A divided by 4. If I wanted to use 10 trapezoids, the height of each trapezoid would be B minus A divided by 10. Well, let's keep it with n for right now. So I'm just going to write the height of each trapezoid is going to be B minus A divided by n. Okay. All right, now, so now in our formula, when we get to it, we're going to be able to replace the h with B minus A over n, where A and B, I can get those from the context of the problem, and of course n is something that I either choose or is given to me for the number of trapezoids that we use for the approximation. Okay, now next, let's say I divide this into n subintervals, and they're along like this. And what we'll do here is we'll call this leftmost point, instead of calling it A right now, I'm going to call it x sub 0 or x naught. Okay, so the height right here, I'm going to call that f of x sub 0 or x naught. And then if I divide this into n trapezoids, right, then this this x value is x sub 0, then x sub 1, x sub 2, x sub 3. And at the very other side, okay, or the very other end of the total interval from A to B is going to be the nth side. Okay, so this is x sub 0, here's x sub 1, x sub 2, x sub blah, 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 blah. And then this last one is going to be x sub n, where n is the number of total trapezoids that we're using here. So this height right here is going to be f of x sub n, again, where n is the number of trapezoids. Okay, so now if you think about it, my trapezoidal approximation then, or the area of the first, let's just talk about the first rectangle first. Okay, I said rectangle, we're talking about trapezoids here. So the area of the first trapezoid would be this. Now I'm going to write this as t sub 1. That's a very common notation to use for maybe the area of the first trapezoid. Well, it's going to be, the formula for the area of a trapezoid is 1/2 times the sum of the bases. Okay, well, first base is f of x sub 0. And then the second base, right here, is going to be f of x sub 1. And then I take that times the height, which is b minus a over n. Okay, so this expression that I have right here should give me the area of the first of n trapezoids. Okay, t sub 2, the second trapezoid, would be 1/2 times, now the leftmost edge of the second trapezoid is the same as the rightmost edge of the first trapezoid. So the first base that I'm going to write here is going to be f of x sub 1, and then the rightmost edge of the second trapezoid will be given by f of x sub 2. And then, of course, the height is for every, the horizontal distance, which is the height of each trapezoid, is always going to be b minus a over n. Okay, now I can keep going, right? The only thing that would change with the area of the third trapezoid would be, the leftmost edge of the third trapezoid will be f of x sub 2. The rightmost edge would be f of x sub 3. Okay, now I don't know how many trapezoids we're using here. Okay, so what I want to think about now is, well, the second to the last trapezoid. Okay, the one right before the last trapezoid. It's not going to be the nth trapezoid. It's going to be the n minus 1th trapezoid. So I'm going to write t sub n minus 1. Teddy, can you see this down here, okay? Not too much glare or anything.
Tn minus 1.
Yeah, t sub n minus 1. Okay, that will be 1/2 times, now, let's think about this. Well, the second to the last trapezoid, this is the very last base of the very last trapezoid. The rightmost edge of the last trapezoid is going to be f of x sub n. Well, the leftmost edge of the last trapezoid would be f of x sub n minus 1. Okay, so that's f of x sub n at the very end. F of x sub n minus 1. The leftmost edge of the second to the last trapezoid would be f of x sub n minus 2. Okay, now I hope that doesn't seem, well, it probably seems confusing. Let me point with a pencil here. Okay, this last base, the very rightmost edge of the last trapezoid, the height is the height of I shouldn't say height, the length of that base is going to be f of x sub n. Okay, the leftmost edge of the very last trapezoid, okay, that right there is x sub n minus 1. Okay, it's one increment before x sub n. So the rightmost edge of the second to the last trapezoid is going to be f of x sub n minus 1. The leftmost edge of the second to the last trapezoid would be f of x sub n minus 2. Okay, so this is going to be, leftmost edge, like I said, is f of x sub n minus 2. And then the rightmost edge of the second to the last trapezoid would be f of x sub n minus 1. And then all times still b minus a over n. Okay, so I've got the area of 3 trapezoids. I've got the very first, the leftmost trapezoid, the second to the leftmost trapezoid, okay, the first trapezoid, the second trapezoid, here's the second to the last trapezoid. What I'd like to do too is write the very last trapezoid. Okay, and I'll write it maybe up top here. So this is going to be T sub n, the area of the very last trapezoid is going to be 1/2 times. Okay, so the leftmost edge of the very last trapezoid is the same as the rightmost edge of the second to the last trapezoid, which is f of x sub n minus 1. And then the rightmost edge of the very last trapezoid is going to be f of x sub n. And then this is still multiplied by b minus a over n, which remember is the height, which is a horizontal distance between the bases of the trapezoid. Now, okay, what we can do now is we can roll this all into one rule. Here's the area of the first trapezoid, here's the area of the second trapezoid, here's the area of the second and last trapezoid, here's the area of the final trapezoid at the right edge of the region. They all have some common factors. Okay, every one of these area expressions has a 1/2 in it. Every one of those area expressions has a b minus a over n. Okay, the only thing that are differs from one expression to the other are the heights of the bases. But even some of those are the same. Because if you look at this, like there's an f of x sub 1 here, and there's an f of x sub 1 here as well. There's an f of x sub 2 here. There'd be an f of x sub 2 in the third trapezoid as the leftmost edge. Essentially, every single base, okay, every single vertical base gets used twice, here and here, okay, except the very first base, f of x sub 0, and the very last base, f of x sub n, okay, because both of those bases, the bases on the very edges of the total interval, they're only part of one trapezoid each. Every other vertical base, okay, like this one right here, that's part of two different trapezoids. Okay, the one immediately to its left and the one immediately to its right. Okay, so now what I'm going to do here, I'm going to erase most of this. And we'll try to roll this all into one formula now. So the area between the curve and the x-axis from A to B is going to be approximately, okay, I'm using approximately equal to symbols. Okay. I'm going to factor a 1/2 out of every single, wait, hang on. Well, yeah, no, I'm right. 1/2. I'm going to factor a b minus a over n out of every single one of those. And then I'm going to open a quantity. And the very first trapezoid, remember, these factors, the 1/2 and the b minus a over n, were being multiplied by f of x sub 0, as well as then plus f of x sub 1. But in the second trapezoid, that f of x sub 1 was going to be used again, this time as the leftmost edge of the trapezoid. So it's going to be multiplied by this twice. It's going to appear twice. So I'm going to write 2 times f of x sub 1. That's a sub 1 there. Okay. And then plus 2 times f of x sub 2 plus 2 times f of x sub 3. And so I don't know how many total trapezoids they're going to have. So I'm going to write plus, and I'm going to put an ellipsis here. Okay, 3 dots to indicate that we're obviously, you know, for the general case, not going to be able to write out all of the bases there. And then it's going to be 2 times the second to the last. Okay. Shoot, I don't know if you can see that. I wrote 2 times f of x sub n minus 1. That's 2 times the base called f of x sub n minus 1. Because that second to the last base is still used twice. Once for the second to the last trapezoid and once in the very last trapezoid. I'm going to have to drop down a line here. And then plus just 1 time f of x sub n. Okay, because that last base, okay, the base that rises out of x sub n is only used once. Okay, so that is the formula for a trapezoidal approximation. Okay, you can use this to do the problems in the assignment. Okay, the problems on the AP exam are not nearly this complicated when they ask you to use a trapezoidal approximation. Honestly, you can kind of throw this out the window if you on the AP exam, the formula, not the concept. Okay, I have an AP exam here. I will email this to you. It's from 2011. But I'm going to erase all this now. On the AP exam, you are better off just thinking about this one trapezoid at a time. I don't know if I've ever seen more than 6 trapezoids, expected in a single problem on an AP exam. But I'll tell you what, and sorry to do this. I was gonna say I'm gonna email this to you right now, but I'll wait till after the video. I'll just recreate this chart up here. It's a fast chart. Okay, so 1, 2, 3, 4, 1, 2, 3, 4, 0, 2, 5, 9, 10, 66, 60, 52, 44, 43. If you absolutely want to pause the video right now and go find this problem, if you go to the AP Central website, this is question number 2 from the 2011 exam. And if you want to pause that, you'll find that. That's the problem that I'm going to talk about here. And I'm really not even going to talk about the whole thing, although I'm happy to at a later time if you want. I'm just going to talk about the part that asks you to do a trapezoidal approximation, which is part B. Okay. So this represents time in minutes, and this is, this is degrees Celsius. This is the differential function h. Okay, yeah, so this is h. I don't know why they use h for this, but h is a function of t. Okay, h is the temperature, t is the time in minutes. Anyway, what they ask you to do in B, it says using correct units, explain the meaning of 1 over 10. Well, I'll write it out. It says explain the meaning of this times the integral from 0 to 10 of h of t dt. Okay, and so I have to think about this. It says up there, all right, I'm going to read the prompt here, and you can go to this problem and read it too. It says, as a pot of tea cools, the temperature of the tea is modeled by a differentiable function h for time 0 to 10 minutes, where t is measured in minutes and temperature is measured in degrees Celsius. Okay. Values of h of t as selected values of time t are shown in the table above. Okay, so this is 1 over 10 times the integral from 0 to 10 of h of t dt. Now, you may recognize this 1 over 10 as being 1 divided by the interval length along the t-axis. Okay, so maybe think back to section 6-5 and recognize that this is going to be an average value expression. Okay, this is 1 over the interval length times the definite integral from a to b, from 0 to 10 in this case, of the function h of t. This will give us the average value of h of t. Okay, so in other words, this is the average value of the cup of tea on the time interval from 0 to 10. If you notice, it starts out at 66 degrees Celsius, so that's a pretty hot cup of tea. Gets all the way down to 43 degrees Celsius, which is a warm cup of tea. But the average value of the tea in the cup on this time interval will be given by this expression right here. Okay, so that's part of it, but that's, we haven't gotten to the trapezoidal approximation part just yet. So the next part of that prompt says use a trapezoidal sum. It's the same thing, with the 4 subintervals indicated by the table to estimate that. Well, okay, so essentially what I have to do is I have to take this definite interval and I have to add to estimate that using a trapezoidal approximation. Okay, that's what a trapezoidal sum means. Before I do that, just a sidebar. Okay, if it says trapezoidal approximation or trapezoidal sum, those two things mean the same thing. Let me tell you something else. If it says use the midpoint rule, that means, okay, and this goes for your assignment too, the midpoint rule means a Riemann sum using midpoints, okay, a midpoint Riemann sum. Okay, but that's not what we're doing here. We're going to find a trapezoidal approximation. Okay, so it says to use the 4 subintervals indicated by the table. If you notice, there's a subinterval from 0 to 2, a subinterval from 2 to 5, one from 5 to 9, and then finally one from 9 to 10. So the lengths of the subintervals and therefore the heights of the trapezoids are not going to be the same the way they would be if you used the formula. Okay, so all I really have to do is find the area of each one of these approximating trapezoids, add them up, and then multiply that result by 1 over 10, since we're asked to find 1/10 of that definite interval. All right, so let's think about this. The first base, or the first trapezoid would have bases that go. One base that rises vertically out of the x value 2, one base that rises vertically, sorry, I pointed at 0 and I said 2. One base that rises vertically out of the x value 0, another one that rises vertically out of the x value or t value 2. So one base is going to be 66 units long and the other is going to be 60 units long. And of course the height of the trapezoid is the horizontal distance from 0 to 2, which will be 2. So I'm going to write t sub 1, which remember is the area of the first trapezoid. It's going to be 1/2 times the sum of the bases, 66 plus 60, times the height of the trapezoid, which is 0 to 2. Remember, that's the horizontal distance there. Okay, so there is the area of my first trapezoid. All I have to do to find that area is to be able to do a little bit of arithmetic. T sub 2 would be, okay, so now it's the trapezoid that has one base that rises out of 2 and another base that rises out of 5. Okay, so that's going to be the area is going to be 1/2 times 60 plus 52 times the height. Now the height of this trapezoid extends the height extends from 2 to 5 along the t-axis or the x-axis. So the horizontal distance between the bases here is going to be 3. Okay. Now t sub 3, and I'm running out of room, and you're probably running out of patience because you think, well, okay, I know how to find the area of the 4th trapezoid and the area of the 5th trapezoid, and of course you do. Okay. Once you have the areas of all those trapezoids, okay, to find the estimate for the integral here, the integral from 0 to 10 of h of t dt, I simply add the areas of those 4 trapezoids. Okay. Then to answer the question in this context, remember they said use a trapezoidal sum with the 4 subintervals to estimate this whole expression, okay, with 1/10 included as a factor here. So I'm just going to take the sum of the areas of the 4 trapezoids divided by 10. I've got my answer. Okay. That's how to do trapezoidal approximations. Listen, as always, feel free to contact me by whatever means necessary. Be happy to help you through any of these problems. I'll email you that 2011 exam. You can look at that problem. You're welcome to do the rest of the 2011 exam for practice as well. For you girls that are taking the AP exam, okay, I highly suggest that you're getting on that website and doing some practice problems, and they've got a lot of support this year as well. I'm happy to help as well. Okay, if you want a video conference with me a little bit, just send me an email. I'll be glad to do that. All right, so that'll be it for today. Thanks for watching.